Alright, so we're talking in this particular video mainly with section 9.6, and we're discussing about what true solutions are, what colloidal solutions are. Alright, so it depends on the solute size, the particle size. When the particle size is so small, invisible, such as tiny ions and extremely tiny molecules, etc., then you can't use a physical process of filtering them out, or using a membrane which is semi-permeable, allows some things to pass through. All right, so the solute can't be separated from the solvent by any of these methods. The only method might be something like evaporation, or and so on. Colloids, on the other hand, the particles are still invisible. However, they're bigger than the particles of a true solution, and they may not be able to be filtered out, but you can use what is called as semi-permeable membrane to separate the particles from the solvent. All right, so the types of colloids depends on what the substance is that is dissolved and what is the medium or the solvent in which it is getting dissolved. All right, fog. All right, think of fog, water vapor in the air. All right, so air, the gas, is the solvent because that's the larger amount, that's the dispersing medium. So the solute, so to speak, the amount that is the substance that is getting dispersed into the larger stuff, is the water vapor, all right, the liquid. All right, so clouds, fog, etc., or hairspray, that would be liquid and gas. Now air has a lot of dust particles sometimes, or smoke. All right, so that would be considered solid and gas. Okay, shaving cream or whipped cream, all right, when you take cream and you whip it up, you're basically incorporating a lot of gas into a liquid medium. All right, so that's a type of colloid where gas is now trapped within this liquid, right? If it is more fluffier stuff, solid stuff like styrofoam or marshmallows, that's gas in solid. All right, milk is basically a liquid. All right, but you have a lot of larger particles, the milk proteins, the biomolecules, etc., present in that. It's liquid and liquid for mayo and milk. However, the solid stuff like cheese and butter, that's liquid within the solid. Okay, and then plasma, etc., that would be solid dispersed in liquid. So table 9.1 lists examples of different types of colloids that occur, that we encounter. Suspensions are where the particles are so large that they are unable to stay in solution. So basically these kind of solutions are heterogeneous, they're non-uniform mixtures, and something like muddy water, or things that you need to shake up because it'll come out of solution, such as like the kaopectate or milk of magnesia and things like that. So those things where the particles are, what is the calamine lotion, those kind of things where the particles cannot stay in solution. When you leave it sitting, they come and settle out of solution. All right, so in these cases, to separate out the particles is easy because you can just filter it, and they all the particles remain on the filter paper, and the liquid stuff comes out, and you can collect the solid from the liquid, right? So in a lot of these cases, these kind of suspensions have to be constantly stirred or shaken in order for the particles to stay in solutions, right? So muddy water, calamine lotion, blood platelets, etc. Those would be considered to be suspensions. All right, to summarize, true solutions or solutions are the particles are very small, and the other thing is a lot of solutions are transparent to light. All right, so light can shine right through it. Okay, particles cannot be separated by filtration or semi-permeable membranes, and the particles remain mixed quite well. They don't come and settle down to the bottom if you leave the solution standing. All right, colloidal particles, the particles are a little bit larger, and these are the bigger molecules like the proteins and the biomolecules, etc. All right, so the particles don't come and settle down to the bottom. For example, milk is colloidal solution, and so the milk proteins and carbohydrates are well mixed in there. They don't settle down if you leave the milk standing. However, those bigger particles like the biomolecules can be separated out using what is called as a semi-permeable membrane. Suspension is where the particles are too large to stay in solution. They're physically even visible to the naked eye, the particles, because they're so big. And so those particles come and settle to the bottom when you leave that suspension standing in one place for too long. All right. In order for these suspensions to be used, you have to constantly stir them or shake them so that the particles go into solution. So you can use a filtration method to separate the particles from the liquid portion. All right, so here you see in this picture, you have a mixture of a true solution, colloidal solution, and a suspension. All right, so if you leave this thing standing, you see all the suspension particles coming and settling down at the bottom of the beaker. Okay, now if you try to filter it, you'll see that the suspension particles, the red, colored in red, the squares, come and settle on the filter paper. All right, whereas the true solution and the colloidal particles come right through and are collected in what is called as the filtrate. Okay, now on the other hand, if you take this mixture and put it into a semi-permeable membrane, a good example would be like something like a cellophane, or like even a Ziploc bag would be considered semi-permeable. And then you find that the only thing that can that can pass through are the particles that are of the true solution. Okay, the colloidal particles remain within the bag, and so do the suspension particles, because they're too big, they can't pass through the membrane. Okay, another key difference is, I did talk about solutions you can shine light through, they're transparent to light. Suspensions, on the other hand, are opaque to light. Okay, they tend to be too dense. Okay, so a mixture that has solute particles that do not settle out but are too large to pass through a semi-permeable membrane would be a colloid. All right, so when you add solute to water, the properties of water, the physical properties changes. All right, vapor pressure, that is the water vapor that collects above the surface of the water, that decreases. All right, the boiling point of the water will go up. The freezing point of water, on the other hand, will come down. So especially in Wisconsin, we can take advantage of that because by adding calcium chloride, right, by salting the roads, etc., we can make the rain or snow, etc., the precipitation to freeze not at 0 degrees centigrade, but below, way below 0 degrees centigrade. All right. So to increase the boiling point, if you add some kind of impurity to pure water, that would increase the boiling point of water. Okay. So pure solvent has a certain vapor pressure. It has a certain boiling point. Water has a freezing point of 0 degrees centigrade, a boiling point of 100 degrees centigrade. All right. Now, what would happen is if you have some kind of impurity, a solute present in the pure solvent, then what you see is that there's less vapor particles gathering up on top of the surface of that of water, of the solvent. All right. This is because the solute particles are preventing those solvent particles from leaving the surface. All right, the solvent vapor particles from leaving the surface. All right, so the amount of the particles up on top of the surface of the solvent is less, and so that lowers the vapor pressure. So if you increase the amount of solute, especially non-volatile, volatile means some volatile would be something like acetone, right? If you heat it up, it easily evaporates. So sodium chloride would be non-volatile. Just by heating up a salt solution doesn't mean you'll vaporize the sodium chloride present in it, all right? So non-volatile solute particles tend to raise the boiling point of a pure solvent. Okay, so more of the stuff that you have, more of the solute particles you have, lower will be the lower vapor pressure, higher will be the boiling point compared to the normal boiling point. Okay, similarly, more particles of salt that you have in water, it will depress the freezing point way lower than 0 degrees centigrade. Okay. Ethylene glycol is added as an antifreeze to the gasoline so as to keep it in a cold weather from freezing up. All right. Okay. So that's one way to depress the freezing point and keep the gasoline still in the liquid state. Okay. All right. So the more particles there are in the solvent, the more lower will be its freezing point or higher its boiling point. Right. So 1 mole of ethylene glycol antifreeze will basically, it doesn't form ions, it doesn't break up in water. So if you add 1 mole of ethylene glycol, it because of hydrogen bonds, it dissolves into water and forms 1 mole of aqueous ethylene glycol. All right. So how much ever moles you add to the water, that's the amount of moles it forms in water. On the other hand, if you take something like sodium chloride, because it is able to break up in water into individual ions, if I just take 1 mole of solid sodium chloride, I'm able to get 2 moles total of particles, 1 mole of the sodium ion and 1 mole of the chloride ion. So I'm able to generate more particles in solution as compared with something which is a non-electrolyte like ethylene glycol. All right. So non-electrolytes generate less particles when dissolved in water as compared with strong electrolytes. All right, we'll stop here and continue this in the next video.